this discussion rather than starting the Vamos seminar.
Happy to do that.
My apologies. I'll mute myself now.
All right, I think we have to start. It's a great pleasure to introduce Vlatko Vedral from Oxford University, who is a quantum physicist. So he works on like multitude of problems, and I just lost track of them while trying to locate his, Google researcher page. But I just want to mention a few things like entanglement measures, quantum information science, quantum discord, quantum and classical correlations. All of these issues at the foundation of quantum physics have been really, it's been a real pleasure to. My favorite result of Vlatko's is his paper on quantum correlations in the system of three interacting particles, which apparently it's a very counterintuitive result. It doesn't have, you can have quantum correlations without classical correlations, which you cannot have with two particles or something like that. So that was very interesting. So obviously at the foundation of everything, but I just want to yield the floor to Vlatko at this point, who's going to tell us about bacteria.
Thanks very much, Timur, and thanks everyone for tuning in, actually, and for inviting me to talk to you. It will be a very simple talk, I think, especially that this is, a simpleton physicist telling you about macroscopic, complex, warm and wet, living beings. So the first part I will really dedicate to simply telling you a little bit about entanglement. It's going to be extremely superficial, really. And then I will, in the second half, tell you about the experiments that we've been working on. And I will give you a little bit of a background on that and so on. So the idea really will be to probe quantum effects in biological systems and even living systems. And most of my research is really in the direction of macroscopicity and the limits of quantum mechanics and whether quantum mechanics can be said to apply to everything. And that's kind of the broad direction into which this hopefully fits. So this very brief intro into correlations is that when you talk about entanglement, the basic notion you're really trying to apply here is whether the state that you're given, and remember the state of the systems that we are talking about, they're really macroscopic, and we're talking about many relevant subsystems there. So this small n could be, Avogadro's number of particles, if you like. But what you're trying to really decide is whether the overall quantum state that you can assign to this system can be written as a classical, these PISA probabilities is a classical mixture of product states. So in a way, there are many ways of saying this. I think the language which kind of I liked a lot when I was doing my PhD as well, is to say that these states can be created by these famous LOCCs, the local operations and classical communication. So, but also another intuition maybe is that this is the kind of quantum physics you will get if you allow each of these subsystems to be fully quantum, but then you don't allow anything quantum across. So there is no entanglement between these parties. In that sense, you can think of that as a kind of local hidden variable, system where your hidden variable is the quantum state. And then you have this probability distribution correlating all of these states. And so as we know, these states are not as useful as entangled states in information processing. And in some sense, I mean, crudely speaking, there's a lot of debate about this. You can think of these states being at the boundary, the quantum classical boundary, because locally they are quantum, but globally they are not. And the kind of difficult question for us is, given a state, on the left-hand side, can it be decomposed in this way? And this is it's an NP-complete problem. Actually, it's intractable. But in some important cases, we do have ways of talking about it, and that's what I want to tell you about. And it's interesting that these ways of witnessing entanglement even work in the macroscopic domain. That's kind of what's exciting, that entanglement doesn't disappear even when you talk about large systems that are in the natural warm environments and so on, as you will see. So this is a Mickey Mouse version of the whole kind of research on these things. But basically, mathematically speaking, we have this yellow set, which is the set of all of these states that are not entangled. They're called separable states sometimes, the ones that I defined on the last slide. And then we have all sorts of entangled states outside. And what we are really trying to decide in this crudest, at this crudest level, is whether a given state is part of this yellow convex subset or not. So that's how a mathematician would phrase this. It's something that's known as the Hahn-Banach theorem. I don't know anything about it, but I know my friends in mathematics dread this as an exam question. I don't know why. To a physicist, this is very simple. Anyhow, you have a point outside of the convex set. And how can you demonstrate that? So a mathematician would say if there is a line or a plane, this would be a multi-dimensional space. So you're talking about a plane in general. If there is a plane such that the yellow set is on one side of the plane and the point is on the other side of the plane, then that point doesn't belong to the set. This looks very obvious. I mean, of course, this is my physicist two-dimensional intuition, and that does look obvious that you should be able to do this. But of course, in physics, this translates into this witness. So W is, of course, a Hermitian operator. That's anything we ever measure in quantum mechanics, and that defines the plane. And then basically what you're looking at is the expected value of this Hermitian operator in your state rho. And being on one side of the plane could mean, for instance, that the expected value, the trace of this operator times rho, is less than some bound B. And if at the same time you prove that all separable states lie on the other side of that bound, then you've conclusively proven that your state is not an entangled state. And I'll give you a very simple example of that. Actually, luckily, many macroscopic observables happen to be good witnesses of entanglement. So we're talking about, things like heat capacity, susceptibility. All of these things actually can be used to actually witness entanglement in many body systems. So that's really what we are talking about when it comes to discriminating whether the state has this very special separable form or not. And probably rather than me talking to you until tomorrow morning about these things, maybe I will recommend this RevMod Phys, which will tell you all about the different kinds of correlations and states and so on. So there are lots of intricacies, but I think for this talk, I will mainly be asking the question, is the state separable or not? In which case I will call it really an entangled state. Now, the tricky bit here, and this will be important for later things that I will tell you, because it will basically determine what we have to do in an experiment to really convince someone that something is entangled. So very generally speaking, you have two requirements to prove that your system is entangled, even at the lowest level. One is that you need to be able to identify at least two subsystems. So you have to be able to somehow introduce this tensor product structure. But physically, what this means is you have to be able to manipulate one of the subsystems without changing anything on the other subsystem. So that's, of course, necessary condition number one. If you can't do that, then it's very difficult really to talk about entanglement. You could talk about superpositions, coherence, and so on, but not really about entanglement. Now, the condition number two, which is also, it sounds innocuous, but it's of course non-trivial, is that we need to be able to measure at least two different complementary observables on each of these subsystems. If you can only measure one observable in each of these, then all you're gonna at best ever be verifying is that the subsystems are correlated classically, but you're never gonna reveal any quantum correlation, as it were. So here is just a very simple example. Of course, any two qubits, if you can demonstrate that two systems are bona fide qubits, then obviously R1 is by definition satisfied. That's one of the kind of Di Vincenzo, if you like, criteria for qubits. But now what you need to be able to do for entanglement is measure the equivalent. I mean, X and Z could be your Pauli matrices, as you know, but they could be any complementary directions, really. And what you need to be able to measure is X and Z on each of these subsystems. And when you put them together, usually what does a very good job, it's kind of equivalent to Bell's inequalities, but without all of these other assumptions that for this talk, we don't really care. We don't care about the systems being too far apart, how quickly we measure them. All of these things are not relevant here. So what we need to be able to measure is some kind of combination of XX correlation and ZZ correlation. And it is simply a feature of quantum entanglement that you can have a high degree of correlation in two complementary directions. And that's kind of the simplest way of putting it. And in fact, what you can show, and this is true for any number of subsystems, is that if you look at the expected value of this witness XX plus ZZ on a separable state, you will always see that it has to be less than or equal to 1. So they're all normalized in the usual quantum information way, these Pauli matrices. And actually, I wrote down even the inequality. It's basically Cauchy-Schwarz inequality applied to this. And you can see that the main point here is that you're looking at the average of the product of observables, which separable states force to be equal to the product of the averages. And of course, this doesn't work if your state is entangled. You cannot say that the average of the product is the product of averages. It's just as simple as that. And you know that a maximally entangled state, for instance, 0, 0 plus 1, 1, any of the Bell states, will simply give you twice as large number as your separable bound. So this is a very simple way. If you can measure the observable XX plus ZZ in your system, and like I said, if you have this solid state system in mind, then you are really measuring 2-point correlations. They are usually equivalent to some kind of magnetic susceptibility or something, if that's the kind of physical system you have in mind. And if you can demonstrate a value that goes beyond this separable value, then of course you have a witness that your state is really an entangled state. So that's kind of the level at which we'll be talking about quantumness here. And then of course I will tell you why even things like this are actually very frequently difficult to do. And then of course there's a question, is the requirement 2 satisfied? That comes immediately from this, because I really need X and Z in both of these subsystems. Here I think I'm just summarizing. I'm giving you maybe another example. So the first one would be this magnetic spin chain, where you have some kind of Heisenberg interaction between nearest neighbor spins, which is really due to Pauli exclusion, as you know. So basically when the spatial states of electrons are overlapping to a high degree, then of course they have to be antisymmetrized internally. And this basically gives you this correlation as far as the spins are concerned. And so this kind of XX plus YY plus ZZ interaction itself constitutes an excellent entanglement witness. And many people have actually done this experimentally because it's easily accessible. The other example I have, and this is a bit trickier now, well, even the first one is tricky if, for instance, you're a D-wave, because in D-wave, you can implement some of these couplings, for instance, but what you can't do is you can't make a measurement in anything other than the Z direction. So then you have to be very careful what kind of conclusions you draw from these kind of things. So, there are kind of various degrees of sophistication as to what you really could do to kind of convince people beyond reasonable doubt that the state really is entangled. When it comes to atoms hopping on a lattice, some kind of lattice sites like the Hubbard model, then you can think of this Z direction as the occupation of the lattice, whether it's empty or it has one atom, for instance. And then particle hopping between 2 different sites would be your XX plus YY. This would be your exchange interaction. And now you could say, well, I could now also talk about entanglement, but the subtlety you might have here, and this only illustrates my point of the requirement number 2 being non-trivial, is that while it's easy to measure whether an atom, I mean, easy for a theoretician like myself, even this is not easy, but let's say it's relatively straightforward to measure whether an atom exists on a particular site or not. The Z direction is very easy. It's extremely hard to measure X and Y because this entails making a superposition of no atom and one atom in one lattice site. And there are all sorts of people who even doubt whether this is possible. I think it is possible if you define your operations properly and all of that, but I'm not going to go into that, but it's an interesting topic in its own right. But some people may say, well, you've got all sorts of super selection rules there, which are prohibiting all sorts of superpositions. I personally, I want to declare immediately conflict of interest. I don't believe in super selections. They're only a question of money. Whether you can superpose things or not, they are not a question of fundamental physics, but that's a different topic maybe. And it's interesting, can anything be superposed? And of course, if you tell me that you cannot measure complementary directions, but you can only measure one direction on each of these subsystems, then, like I said, it's very hard to make a convincing case that this state really is an entangled state. And so now I want to go into the main topic really. And the way I'm motivating it here is, I mean, you can motivate the transition to classical physics in many ways. Again, I can declare another conflict of interest. I think treating the whole universe quantum mechanically is perfectly consistent at present. It's also consistent with all the experimental results we have. So I don't believe in any measurement problems or any other problem out there. That's yet another topic that we may want to touch on later. But my motivation really is a physics. Even though I'm going to be talking about biological systems, I'm really going to be checking whether even living systems could, in some sense, be superposed or entangled. And this is interesting because, as you know, there are all sorts of theories out there which actually suggest to us that you may not be able, there may be a limit to how quantum systems could be, depending on their complexity. So what I'm going to do is, because this leads me naturally into the second part, I'm going to make a very brief stop and just check if there are any questions on this first part of the talk.
Yes. So there is a couple of questions. So is it, Shimon is asking, is it reasonable to expect a large system to ever be separable, given that interactions between the subsystems will presumably result in entanglement building up over time? I have always thought about decoherence as a subsystem becoming entangled with a much larger system, and we call the environment, and trace out, so that does any subsystem become entangled eventually?
Excellent question. Yes, this is of course a very big and interesting topic. And I think you are right. The intuition is correct that if you could eliminate thermal noise, I'm speaking very crudely now. So if you really cool your system down close to the ground state, then, and in fact, this is going to be very similar to what I will be telling you as far as the experiments are concerned, then of course, you can almost always guarantee entanglement because the interactions are almost always on between these constituents. Now, of course, as you ramp up the temperature, of course, it doesn't have to be just temperature. It could be couplings of all sorts of other kinds with the environment that give you an effective temperature, if you like, any kind of noise. Then there will be a trade-off between the strength of your interactions within the system and the coupling, the strength of the coupling with the environment. And again, very crudely speaking, that's where the boundary is. You know, if the energies that are related to your coupling are greater than with the environment, you will, again, broadly speaking, be able to witness some kind of entanglement.
All right, so we have a question from Aziza. She is asking, and that is actually a question that's shared by, I think, many of our viewers. Could you please remind us about super selection, what it is?
Oh, yeah, sorry, that's a good point. Super selection, I think the name comes from, of course, selection rules are the ones in the atomic physics because due to all sorts of conservation laws. And then of course the question arises whether even given any kind of resource on the side, any kind of reservoir in the state that you can prepare, whether there is a limit to what you could be superposing. Maybe the most famous, rather than talk at a high level about it, the most famous example of super selection rule is that you cannot superpose even and odd numbers of fermions. This is a very interesting, I think Wigner was the person to actually highlight there. In fact, you're going to get into trouble with microcausality if you assume that you can have one electron plus two electrons in the same state. Even 0 electrons plus 1 electron is prohibited. Another way of saying this is maybe that you're never going to be able to superpose a fermion and a boson. Again, I kind of am leaning on the other side of this, that it's not entirely obvious to me whether this is a rule that's true for all practical purposes, but may not be ultimately fundamental. But the super selection rules would be basically prohibitive statements as to what you can superpose in nature. And it's a huge subject. In fact, I can recommend a couple of nice reviews on this topic as well. And I think there are people on both sides of this boundary arguing both ways, basically, that there is no limit to superpositions, or yes, there is a limit.
I just had a point, like a hydrogen atom. Like, wouldn't that be, let's say, deuterium atom, would that be as if a superposition of somehow electron and nuclear fermion and boson in a way, right? As a combined system, interacting system with a fermion and boson. Like deuterium.
Yes, but I think what you want really is one particle that's a fermion and a boson coherently. That's the question.
Oh, okay.
Not two particles, but you really want some kind of off-diagonal elements between the fermionic and the bosonic system.
Okay, so it doesn't have to be composite system, but so
it's not a composite. You're right.
As we speak, there's there's a new question about super selection that just been added. And that is asking, are there experiments that could answer the question about super selection?
Yes, I think I had a few proposals how to, for instance, how to even superpose an empty site in a potential well with a single atom sitting at that site. They usually involve having reference systems. In this case, for instance, if we're talking now about bosonic atoms, we would have a Bose condensate as our reference system that has to couple to this system to drive these transitions. And then any coherence or any superposition that you claim you make has to be done with respect to this kind of reservoir, if you like, which provides your reference. So it's in direct analogy to thinking about a two-level atom and superposing the energy levels of this atom by shining laser light onto it. So the laser light provides the reference for your superposition in the same way that a Bose condensate would provide the reference for this kind of number state superpositions. So I think they are good qubits, as good qubits in principle as anything else. It's just that it could be much harder to make these kind of states.
Okay, so I guess we can just move on to the second part.
Great, thank you. So I'm gonna use Niels Bohr. I'm gonna probably read this out to you, otherwise there's no point in me talking. So I think the motivation is interesting because most of you will know that Niels Bohr applied complementarity to almost anything that he saw. Once he saw that this was the case with quantum mechanics, then he started to see it in all sorts of other areas, including, psychology and sociology and all of that stuff. But certainly in biology, incidentally, I'm not a great fan of his interpretation of quantum mechanics, but that's besides the point. So here is what he said. He basically saw complementarity in living systems, and it's to do with somehow the chemical processes versus organization of living systems. And if you read the second paragraph, the study To study the chemistry, the organization had to be destroyed. To study organization, one has to operate at the level at which chemistry is invisible. So Bohr proposes, this is a famous set of lectures, I think in Copenhagen, Light and Light. It's a very nice read, actually, lots of crazy ideas there. But Bohr proposed that the chemical basis of an organism and its organizational hierarchy are complementary properties. So I put a very crude spin on this, that you cannot have something alive and quantum mechanical at the same time. And that's kind of what I want to proceed to refute, if you like. I'm kind of saying chemistry is really all just quantum mechanics, as you know. So I'm treating chemistry as a special application of quantum mechanics, which is why I kind of distill out of his statement that he would say that if you want to probe the nitty-gritty of living systems, they can no longer be alive, actually. I'm not sure if you read this statement in the same way, but anyway, I'm just offering it as a motivation. At some point, I was actually, about 10 years ago, I was exceedingly lucky. There was a number of fortuitous events that happened that made me go in the experimental direction and actually start to grow an experimental activity in my group. And one very lucky thing that happened is that I met a person called James Martin. And James Martin, philanthropist, gave the largest donation to Oxford in the last 500 years. I think he gave 200 million. He didn't give all of that to me, but he was actually nice enough to give me about 1%, maybe a bit more than 1% of that, which was still a lot of money. And he was very fond of these kind of ideas of pushing quantum mechanics from the micro into the macro domain, also very fond of quantum technologies and all of that. So I was very lucky to meet a person like that. And then I was lucky that I was somehow reconnected with two very good friends of mine who were experimentalists, and you will hear about them. Dave Coles is the person mentioned in this slide, and he's actually the person who did this experiment that I will mention now. He literally put individual living bacteria into microcavity, optical microcavity. You will have a few slides on that in a second. And then he confirmed what we call the vacuum Rabi splitting, that there is a very strong coupling between the bacteria and the light inside this cavity, the modes inside the cavity. And that's kind of going in this direction of having a living system become quantum entangled in a very specific way, and admittedly possibly not as impressive as it could get. And that's kind of the long-term vision that I want to tell you about. Let me show you a little bit what Dave did. This was a sequence of experiments. I'm describing maybe the last one in this sequence. Is that this is these are some images of the bacteria in the part A. Part B is basically fluorescence, both from the bacteria. So the experiment evolved over a very long drunken session where Dave and I went to a pub, and I think as I was drinking, I was suggesting crazier and crazier things to him. And to my surprise, every time I would say something, they would say, well, maybe I can do that too. So I can show you how far we went. And I was extremely impressed that actually he had this amazing positive attitude that maybe these things could be done. So the idea was really to have bacteria alive and strongly coupled to light. And then the question that we were really asking is, how do we know that they are alive? My initial idea was to check whether they are multiplying. I thought if you're having sex, you're probably alive, actually, but it turns out that there is an easier way of doing this. And the idea is to inject a dye molecule, which is the purple molecule in the inset C, which actually fluoresces differently to the bacterium. And in fact, you can tell whether this dye is outside of the bacterium or inside the bacterium. And that's a very crude way. When the bacterium dies, it no longer maintains its own integrity. There is one of those Greek words that biologists use for that, ancient Greek. And that's basically our crude witness of being alive. If the dye is outside of the bacterium, then everything is nice. And if it's inside, that kind of concludes that they are no longer alive. So these are the usual light harvesting bacteria that you may have heard a lot about. They're the green sulfur bacteria. The experiment is a room temperature experiment, of course, because they have to be alive. You could cool these things down. You could extract bits of them, as you will see, and cool them down, and people have done all sorts of things. But what we really wanted to show is that we can have the system function normally and at the same time be to some degree quantum mechanical, whatever this is. Would you like me to stop for a few more questions at this point?
There is a couple more questions, but well, there's actually one question, question from Erin Steinberg, which I can ask. The question is, can we about the Coles experiment? You can say the bacterium is being alive and being in a superposition at the same time, but really you're discussing independent degrees of freedom. No?
Absolutely, and I think it might help for me to show you the exact picture now, and the next slide for you to see exactly what's at stake. Like I said, I'm a simpleton physicist, like most of us, I suppose, and I usually try to view these systems as qubits, you know, or at best 3 or 4 level systems, and you are of course targeting a very specific transition to which you are meant to be strongly coupling. So even though I call this macroscopic entanglement, because the system is a large system and even functioning, like I said, of course, when you talk about the relevant degrees of freedom, they're always almost invariably small in all of these experiments. So I don't know if this answers your question, but maybe I can just take you through the picture, through the relevant energy.
There's a clarifying comment following up. So it says that if instead of describing subsystems based on which bit of matter is in them, we did based on a more reasonable Hilbert space decomposition, wouldn't we say there is a center of mass degree of freedom, which can be in superposition, but has nothing to do with whether the bacterium is alive or not, and internal degrees of freedom which exhibit life?
Great, it's a great question. I will get back to it actually. This was towards Dave's and mine last part of that session. I think the pub closed and we went to my house, and I was suggesting follow-ups to these experiments, and I think what you're mentioning now resonates very much with what I have in mind. So maybe I will come to that as well. It's a very good point, in fact. Shall I, if I continue with this picture? Excellent, thank you. So basically, I don't know how familiar you are with all of these things, but of course, the bacterium absorbs, that's exactly what they specialize in. They are extremely good absorbers of light. Some of these bacteria live 1,000 meters under the surface of the sea. They get a handful of photons per hour, basically, and you know, they wouldn't be alive if they didn't catch each of them and be able to convert it into energy. So they, of course, capture light at some frequency, at some wavelength, and this actually is dependent on this antenna, and all of these antennae are different from bacterium to bacterium. So all of these frequencies will vary a little bit. And then, of course, when the photon is captured, it cascades down the energy levels. I think I only put down the relevant energy levels that were strongly coupled to the cavity that Dave Coles was using. So basically what happened is that in a non-radiative way, this exciton, if you like, goes down and loses energy. So basically you end up with a larger and larger wavelength here until finally it ends up somewhere along here. You will see this famous or infamous FMO complex that people at Berkeley, among others, Graham Fleming, I think, made this famous in our field by claiming that this is a quantum mechanical process. So this FMO complex is a bit like a nanowire that has almost 100% efficiency in transferring the exciton from the base plate to the reaction center. And then when it gets to the reaction center, it triggers the ATP cycle, and most of that is chemistry. Really is not interesting to us quantum physicists. I'm making fun of it, actually. I think probably even important aspects of the reaction center are genuinely quantum mechanical. In fact, we need more quantum physicists to go in this direction, because biology is probably far too important to be left to biologists. And I think that, seriously speaking, the next 20 years of science will probably see this very big convergence of all of these sciences that for the last 200-300 years grew very separately, but now really are getting unified as physics is going into, I think, more and more complex systems. Anyhow, these are the relevant energy levels. And what I'm going to make a very quick comment here. I don't want to bore you with any of this, but as you go into modeling the transport here, you almost invariably end up using solid state. You know, the typical models from solid state. Here is the famous Holstein model where you have some hopping. I'm showing it to you because it's related to these witnesses as well. You have the hopping XX plus Y with some kind of energy T. Then you have omega M, which are basically the frequencies of your phonons. Phonons are always very important because it's very hard to insulate the system from the vibrations, and they come as one package. Then this first part of the Hamiltonian are the energies of the individual sites, and the last term is really the coupling of your exciton or electron or whatever else is flowing there to these phonons. And what's extremely difficult to us, even this model, even though it's got only a handful of parameters, what is extremely challenging for us is to even determine the G's and the omegas and the T's in a complex system like the mitochondria, or this complex number 1 that I'm showing you here, or indeed the FMO complex. And there is usually some kind of suppression of this T, of the tunneling between different sites, that comes from the entanglement between your system and the vibrations. And the parameters you really need is G, which is the coupling strength to the vibrations, and omega, which is the frequency of these. And they're extremely hard to even determine because these systems are extremely messy. I'm digressing literally one more slide to show you how bad our estimates of these were. And notice that how quickly you get from one end of the chain to the other is exactly dependent on the size of this T. It's inversely proportional to T. So basically having an exponential in front, which exponentially depends on these two parameters that we don't know, is a bad news for us, because even a small error in G's or omegas could actually make a large error in the estimate of the times it takes for the energy to go from A to B. So it's really a nightmare for a physicist, this kind of environment. And so we did some basic input-output spectroscopy. You know that you will be absorbing energy at a higher frequency, then you will be in a non-radiative way losing this frequency due to all sorts of vibrations inside the molecule. And then finally, the frequency that you will re-emit will naturally be smaller than the frequency. This is the so-called Stokes shift, if you do this kind of stuff. And basically Tristan Farrow, another experimental colleague of mine that, like I said, I was very lucky to reconnect with it at that time, would be doing something like this to really fit a typical Lorentzian curve to tell us the gap between the input frequency or wavelength and the output wavelength, which to some degree would tell us what this omega is, what is the typical vibrating frequency. And then we had all sorts of other methods to estimate G, but ultimately, even in an experiment like this, we had about a 6 order of magnitude uncertainty in the final estimate of this hopping rate, T. So it was highly inconclusive. You know, it could be anything between a nanosecond and a millisecond, basically, from one end of the chain to another one. And it's really frustrating that there are no other experiments that could actually, in many of these systems, determine this more precisely. Anyhow, back to the bacteria, which is a much simpler model. I'll show you what we did here. So this is what Dave was doing. Dave was changing the length of this microcavity in order to bring the modes inside the cavity strongly on resonance with the transition, this highest level transition in the first case, and then the one down and the one down that I showed you on this energy diagram of the bacterium. And what happens, if you're familiar with this kind of effect quantum mechanically, is that we get something that's known as vacuum Rabi splitting. So when two systems that are coupled to one another, in this case, we have a bacterium and the mode of the cavity. When they are very far of resonance, then basically you can just simply assume that the energy is the sum of the two energies. There are no cross terms of any kind. And now as you start to bring them into resonance, the levels that would naturally cross, that would be degenerate because of the coupling, actually avoid one another. And from this avoidance, you can estimate what's known as the Rabi frequency, which gives you this vacuum Rabi splitting, which is a witness, if you like, of the strong coupling between the bacterium and the mode. So I think coming back to one of the questions here, what is entangled here is actually the whole bacterium, which I'm modeling as a bunch of dipoles. I will show you that on the next slide, with a single mode of this cavity, one of the modes of the cavity. As you can see, this changes as you vary the length of these cavities. So it's very interesting. It's a kind of molecule, but it's a molecule that's formed from an exciton on the one hand, which is basically this electron excited inside the bacterium and undergoing this transfer by coupling to the phonons as well, and light inside one of the modes of this cavity. So it's a kind of molecule, if you like. I'm abusing the language, but it's a molecule that's a kind of hybrid molecule. It consists of half light and half matter. It's known as a polariton, if you like, in the language of people who do this kind of stuff. And what was greatly interesting to us, like I said, is that you can see these bacteria even under a microscope. You can see that they are alive. You can clearly discriminate the signal that comes from the dye with the signal from the bacterium, and that was really the big deal in this experiment. So let me give you the Hamiltonian, and then maybe I make another short break before I tell you about some possibly crazy stuff. So we went with the extremely simple Hamiltonian. So you can read a lot more in these papers that I'm citing. I don't really want to bore you with all the details, but what we did is we simply assumed that a bacterium, each cell in a bacterium has a number of these dipoles, if you like, that I modeled very crudely as a two-level quantum system. So when you add them up across the whole bacterium, you have about 100 million dipoles. This is something that's known as the Dickey model, if you want the precise word from physics. So you've got about 100 million dipoles, all coupled strongly to a single mode of the optical cavity. That's kind of the right way. And because there are 100 million dipoles, I'm making an approximation, but it's so good that you're never going to tell the difference. I'm kind of calling that a harmonic oscillator. I'm taking 100 million qubits and calling them effectively an infinite dimensional system. And so A and B are simply all of the dipoles of the bacteria, and the other one is the mode of the cavity, which is a genuine harmonic oscillator. So that's your first, the first two terms of the Hamiltonian. The last term, of course, is the coupling term. I should be using probably omega instead of lambda, but that's your famous Rabi frequency that couples these dipoles to this mode of light. And as most of you will know, this is the usual electric field E coupling to the dipole, and then times the square root of the number of these dipoles. And actually, if you want to know the strength of the Rabi frequency, you can read it off directly in each of these cases for these different energy levels. It's given in terms of milli electron volts, but basically that's your h bar omega, if you like, or h bar lambda, as I call it in this model. So again, what's exciting, and I think someone asked this question, what's exciting is that, of course, the ground state of this system is something that we studied a lot in many body quantum information. And the ground state would be one of those highly entangled states. But what we are measuring here is the splitting between different energy levels. We are not really confirming entanglement in the ground state. The ground state would be such a state where you would have n photons in the cavity or n excitations inside the bacterium summed over all possible values of n with specific amplitude Cn. So basically, if you were to find the ground state of this kind of Hamiltonian, it would be of this kind. But like I said, this is the kind of entanglement that is very hard to get to because the light and the bacterium really come packaged together as almost one quasi-particle. It's very hard now to split them apart and to say, let's measure one and not the other one, and so on. So this is where this first part of the discussion was relevant in order to set the scene and to say this is what's possible to do and this is what's not possible to do. And actually you can even measure entanglement, like I said, because there are many papers in the field that quantify entanglement exactly in this kind of system, and they tell us how entanglement grows the closer you get to the point of phase transition, which actually we could also find in the experiment, and we could map exactly the right number that was achieved as far as entanglement is concerned. Of course, if you believe that this is the right ground state for this kind of experiment. So maybe I'll make a 1 or 2 minutes break just to allow for a few more questions if there are any.
All right, so actually I had a couple of questions. That was a very nice Hamiltonian, but the bacteria, right? So I was just wondering if there's like a life parameter or something that tells you like if the bacteria is alive or not. Like
the only, you know, biologists have these kind of witnesses of being alive, right? And you kind of always smile at them as a physicist, right? Because biology is just far cruder, too unsophisticated in a way for a physicist. But one of them is really that the system maintains its own integrity, right? So any foreign bodies like a dye molecule would actually be kept outside of the bacterium. So admittedly, this is a very, very crude witness of being alive, but apparently if you detect this molecule inside the bacterium, then you can be pretty confident that the bacterium is no longer alive. So all Dave was doing is really getting the spectra from the fluorescing molecule at the same time as the bacterium to make sure really that the two are separated, if you like. Mm-hmm. I'm sure there could be many better ways of doing this, but I'm not sure if they would be easier to access.
I see. So maybe, I mean, I don't know, if you can feed something to this bacteria and then it will swallow it, then it will probably like...
That's what I was suggesting, kind of to see whether they grow, and then it could have an effect on your signal as well, of course, because you'd be shining light through a thicker sample, possibly at some point, and so on. But I think it seems to me even more difficult than this simple dye witness.
I see. And another question I had was, so this is a very like laboratory kind of experiment where you have this highly idealized,
yes,
very coherent, perhaps,
yes,
or is it a Fock state that you have in your cavity, perhaps, but or a number state, but
yes.
Sorry, the coherent state. But the point is that under their natural conditions and habitat, they have this incoherent light, which is nothing like a Fock state or a coherent state. So
yeah,
how relevant is that to what they actually...
Absolutely, great question. Excellent question, Timur. Actually, I don't have an answer to that. I think this is going to be one of the speculations on one of the last slides. I think I'm very close to that. So maybe I'll wait with the answer for that. But I think you are modifying the modes. You are right. Under normal circumstances, the bacterium sees what we would call the usual continuum of the electromagnetic modes into which it can emit. What you are doing now is the so-called Purcell effect. Again, if you're an experimentalist, you'll be using all of these words. But what you are really doing is you are tailoring a very specific density of electromagnetic modes inside the cavity. So you are right, this is a hugely artificial environment. This is not what the bacterium would normally see. So I think one has to be extremely careful what one concludes about the functionality. You know, is this really relevant for the functionality? I think it's an excellent point.
Thank you. And there's no more questions as far as I can see. So
maybe I continue, and then I think we will naturally probably reach this. So in fact, I'm coming to that. Like I said, vacuum Rabi splitting is the equivalent of measuring XX plus ZZ kind of witness. In this case, of course, you'd be calling this witness A dagger B plus AB dagger, if you like. It's the exchange operator between two strongly coupled harmonic oscillators. And like I was saying, you can get away with this approximation because the exciton inside the bacterium lives for sufficiently long. I think we're talking nanoseconds, even larger, that's been observed in the experiment. And the light that you're detecting from a cavity, in fact, comes out much faster, 3 or 4 orders of magnitude faster than that. So actually, you could really guarantee that you're in this strong coupling regime, and that the results that you are getting are really confirming what you believe they should be confirming, like the vacuum Rabi splitting. Now, what would be more convincing, and I think this is what we would like to really do next. So I will tell you kind of what we are preparing ourselves to do. I'm hoping that that someone gives me another couple of million, and that we can do a lot more fun stuff. I'm not asking you guys. I know we're all in the same boat as far as the funding is concerned. Anyhow, I've been lucky to have lots of private individuals giving me money. I hate applying for grants with the governments and all of that. Anyhow, different topic. If you could do resonant Rabi flopping, you know, if you could repeat the Arroche experiments, the Nobel Prize winning experiments of an atom coupled to modes inside the cavity, and then get some coherent flopping between light and this atom, this would already be next level up as far as quantum effects are concerned. So you'd effectively be doing a NOT gate, if you like, in a coherent way. There's no reason why you shouldn't be able to do that. In fact, the difference being, of course, is that now you need to drive the system with a coherent laser light. So I think Timo may not like it because it's becoming even more artificial than the natural white light that the bacterium would be seeing from the sun. And then you can kind of get crazier and crazier in the sense that you can say, is there a way to somehow really separate these degrees of freedom? I mean, can we think about that? Could we really measure independently X and Z on 2 of these subsystems and get something really to violate Bell's inequalities or to be genuinely entangled and so on? So these are all the things we would like to do. I want to give you one word of warning before I show you these kind of experiments, what we are planning to do, and then maybe there would be an interesting discussion. Whenever you do these kind of things, there's always a complaint that you can account for your results classically. This is certainly true for the transport in Fleming's experiments. You can actually have a chain of coupled harmonic oscillators. So I just jotted a few things down here for you to remind you of how this is done. So basically, I have a Hamiltonian for 2 dipoles. Let's say these are 2 electrons that are somehow attached to nuclei. So here is the kinetic energy. Here is the restoring energy. So the size of the dipole, each of the dipole is A. Then they get kicked a little bit, X1 and X2, and there is a restoring Coulomb energy. And then there is a dipole-dipole interaction. That's your typical Hamiltonian. This is classical Hamiltonian so far, by the way. Now, if you diagonalize this Hamiltonian, you're going to get 2 frequencies. And actually, if you match these parameters to the experimental one, you can get these frequencies to exactly give you the gap that you observe in the experiment. So whenever you do this experiment, people say, but look, I can do it classically. So you're always fighting. That's why I'm saying, if you want to go beyond reasonable doubt, we usually need to do more than that. Now, the interesting twist here, this is one of my favorite models, actually, because the question then becomes, not only how to convince yourself that it's quantum, but is it non-trivially quantum? What does it even mean? You know, in the whole of chemistry, like I said, is quantum. Atoms wouldn't exist without quantum mechanics. Molecules wouldn't exist. So where do you draw the line? Where do you say, oh, this is quantum beyond reasonable doubt, if you see what I'm saying? Now, the interesting thing about this Hamiltonian is that to get the van der Waals force, you cannot leave it classical. And that's the interesting thing. And you can go back to 1937, a guy called Fritz London suggested that. And it's a mind-blowing idea, 100 years old, but mind-blowing. What he said is that if these oscillators were classical, then the ground state would simply be when all the x's and all the p's are zero. And it would be zero, basically. But because of the uncertainty principle, because of the vacuum fluctuations, because you cannot specify x and p simultaneously, the sum of the vacuum energies, in fact, to the first order gives you the van der Waals force. So van der Waals force is only possible quantum mechanically. It's very hard to account for all the features of van der Waals if you're just a classical physicist. And the reason why I'm mentioning this is because, so do you consider this effect trivial or not? Who knows? But when you have spiders, I'm going to say even large spiders, you have this jumping spider. And you have a very shiny metallic surface, and these guys can crawl up despite the gravity. It looks incredible. They can stick to mirrors, to shiny mirrors. How do they do it? And actually the answer is very interesting, because these mirrors to us, of course, look very frictionless and shiny. But if you zoom in, you will see lots of small holes and cracks and so on. And this is the reason why spiders have hairy legs. I mean, I have hairy legs as well, but I'm too massive for this kind of thing. So spiders have hairy legs. And when these hairs, they're small enough to be able to go inside these cracks. And when the molecules from the hair are close to the molecules of the mirror, they actually start to bond in the van der Waals way. So actually, next time someone asks you, how can a large spider crawl up a mirror? It's because of the quantum uncertainty principle, right? That's always the answer. It's one of those jokes, but in this case, it really is. So now, do you call this trivial quantum effect? Is this trivially quantum because it's part of our molecular structure understanding and all of that? Or is this just simply amazing? Is this just an amazing macroscopic effect? So there are always, I'm just raising this because there are so many subtleties when you go into a field like this, but also many, many fascinating things. And here is more or less the last thing. I don't want to bore you too much, but because there was a question, one possibility, if you're thinking with a kind of application in mind, is to really ask whether I can bring bacteria even more on resonance with the light that it absorbs. So there are two aspects there. Maybe I can make the bacterium even more resonant by tuning it correctly with the cavity, or maybe I can make it so off resonant that I kill it quantum mechanically. That's why I coined this nice word there. Quantum bactericide, right? So what's interesting to a person like me, and you all know that I'm coming from the, physics is the queen and everything else is just a servant of physics, really. So the direction I'm coming from is, can I really do Schrodinger's cat experiment with the bacterium? Can I really simultaneously detune it in the right way and in the wrong way? What would this even mean, in fact? So there's lots of interesting questions you can start to ask there, but the fundamental idea is really, does quantum mechanics even apply to all of these things? And I think the papers I'm citing here are not relevant for this, but they're really applying quantum. So there are all sorts of quantum thermodynamics ideas that come in. And in fact, the biologist would tell you should probably use some thermodynamics, not just quantum mechanics, in order to understand these systems, because they are really kind of Maxwell's demons, right? They're trying to convert energy into something useful, one type of energy into another one. So here is the final picture. What we are aiming to do next, we are practicing with non-living systems. They're much easier. You can cool them down to low temperatures, in this case, 4 Kelvin. Liquid helium or below. Of course, then you eliminate lots of vibrations. But what we want to do is really make an optical interferometer where in each arm of the interferometer we stick one cavity. And in each of these cavities, there is one of these organic molecules. And now you're really playing with Schrodinger's cat idea. Every experiment in quantum physics is Schrodinger's cat experiment, as you know. There are no other experiments. They could just be more or less complicated. So here you have a single photon split at the beam splitter. It goes both ways. Then it gets absorbed by one bacterium and not the other one, or vice versa. And basically that's an excited ground plus ground excited state in our language. It's a maximally entangled Bell state, and that's what we are really aiming at. The subsequent part of this experiment looks extremely complex. I don't even know exactly to what degree I could confirm this entanglement and how far I could go to design complementary measurements, and there are many difficulties there. But the interesting thing is that you could actually scale this up as well. So there is a colleague of mine here at Oxford who actually, Jason Smith, who in fact engineers this kind of microcavities, arrays of macrocavities. You can go into his lab and he presses a button, and after 1 second you get an array of this kind in the slide in the lower right-hand corner. And so basically you can now even imagine entangling a bunch of these molecules that could each be hosted in one of these cavities. So that sounds to me also like an interesting idea. Some of my colleagues, I'm like I said, I'm brutally a quantum physicist. I actually don't really care about many other things in that sense. This is kind of the most exciting question for me. But of course, for quantum technologies, you could think that some of these qubit suggestions, not with living systems, probably would be also of interest. So let me leave you with these conclusions. In the sense that, and I think one of the questions, I think you will see most of it is just a summary of what I said, but I think Timur raised this question of, and this I think is a fantastic thing to try to answer, which is, are these quantum effects really somehow, have they deliberately evolved, whatever this actually even means, as you know? So, did evolution somehow have a pressure, if you like? Was there an evolutionary pressure in the direction for the system to really improve its quantum information processing? Of course, no one expects a universal quantum computer inside the living system, but some of these specific computations, I think, would not be crazy to suggest that they could be really quantum coherent. I have no idea how one could answer this question. Maybe there could be some kind of genetic modification of the system which changes the structure, and then checking whether quantum effects vanish at the same time when functionality disappears, or things like that. So I think this is a beautiful question. It's again something that a biologist would be very, very interested in. And then the final point is the one that Schrödinger raised a long time ago in his book, What is Life? Do we actually really need to even change our laws of physics in order to understand living systems? Everything I've seen so far would suggest no, but of course for us it would be much more exciting if the answer was yes, because quantum mechanics has been depressingly successful in the last 120 years, and we are all kind of secretly hoping it collapses. I mean, I'm not hoping in this stupid classical way that it collapses, but I'm hoping that we get some evidence from experiments that we need to do something even crazier than quantum mechanics. But at the moment is good enough, I would say, for biology. Thank you very much.
All right, thank you very much, Vlatko, for the wonderful talk. We have a couple of questions. So Mohammad Hafizi is asking about Rabi oscillations. Could they be understood in terms of two coupled harmonic oscillators with a coherent exchange, like the mode splitting in a resonator?
Yes, it's an excellent question, and the answer is almost certainly yes. So here, what I had in mind is something slightly more complex, namely to add another harmonic oscillator. So the two harmonic oscillators would be the host of dipoles inside the bacteria, one, The other one would be the mode, the resonant mode in the cavity. And the third coherent state, in this case, if you like, the third harmonic oscillator would in fact be the laser that you would tune to be in resonance with the vacuum Rabi splitting that arises from the first two systems. And that's kind of the transition you would like to drive.
Vlatko, let me see if I can clarify Mamad's question a little bit. You can understand in linear dispersion analysis the vacuum Rabi splitting as coming from two classical coupled oscillators.
Yes.
So if you're driving the cavity with a coherent state, which is a classical state, I think the question is, in what sense are you generating any entanglement whatsoever?
Yes, I think you, excellent question. In fact, this does not quite answer the question I raised about entanglement in the eigenstates of the cavity and the bacterium, if you like. Because what you're doing is you're taking this structure as a given now. So you're right. I'm not suggesting that this would confirm that the ground state, for instance, is entangled, or the first excited state is entangled. All you are demonstrating here is that you can coherently make a superposition of two of these Rabi vacuum split levels. So you're absolutely right. This would be a very different kind of coherence to the one that you may have in the entangled state between the dipoles and the cavity. It's a very good point. That's why I said we probably need to go even more beyond that and somehow be able to address these systems independently, which is why I thought having two organic molecules would at least allow me to be able to probe them individually. And of course, with atoms, these experiments have been done in a number of different ways.
Okay, and the final question comes from one of our panelists, Monica. Can we envision accessing a regime where you can observe effects of quantum fluctuations in the number of excited dipoles?
Oh, that's also a very interesting question. So here I would really say that this number is huge. I understand the question. This is a beautiful question because actually, when we talk about entanglement in systems of many qubits, let's say like cold atoms and so on, then we could use some of these squeezing type witnesses to actually say, well, there are some kind of fluctuations already within this system that we can reveal. It seems to me that at least this bacterial system is really too complicated for me to see how to do this within this experimental setup. But I don't see in principle a reason why this couldn't be done. You're right, this would be yet another witness of yet a different kind of entanglement, in fact.
Sorry, this is all for questions. Could Vlatko, can I ask you to quickly unshare your screen, please? Because I need to make an announcement.
Of course.
The next week seminar. So
is that okay now?
It seems that it is okay. I'm trying to share my screen, but let's see. Next week we're going to have, let's see, share if I can get, I don't know if you can see these upcoming talks from Quantum Science Seminar on exploring quantum non-equilibrium processes with synthetic quantum system by Igor Lisanovsky from Germany. And Waymo's talk next Friday will be by Kater Murch from Washington University of Topological Control of Quantum States. So there will be more discussion, hopefully following up in like post-seminar. So please see the link in the chat. And thank you very much for all attention. Thank you.
I'll see you shortly. Thank you.